Hi, so today's lecture will be on bijections. Now, some of you may be wondering, what's a bijection? It sounds really funky. In simplest terms, a bijection is a one-to-one correspondence between two sets. So visually, if we call this set A and set B, if we make a bijection from set A to set B, that means every element in set A has a mirror image in B. So we can make this heart. And one-to-one means that every one in A has a twin in B. This is called a mapping, and this picture represents a bijection. And bijections determine the cardinalities of the sets. So if you know how many elements are in set B, you can find out how many elements in set A. And this can be used to solve a lot of counting and probability problems. Let's start out with an example. How many paths are there in this 3x2 grid from point A to point B? Let's say there's a person who needs to get from point A to point B. How many paths are there? Do you guys know any ideas on how to start? Yes. Okay, so, oh right, there are conditions for this traveling. You can only go to the right and up. You can't reverse your steps. So you know that if you start drawing out a few paths from A to B, this is one path, right? And there are 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 steps in the path, right? So let's draw another path. How about we go, there are also 1, 2, 3, 4, 5, right? So if you keep doing this for a little bit, you'll see that every path from A to B has 5 steps. And every of the steps, how many of them are going to the right? 2, right? How many of them are going up? 3. So you notice a pattern here. And instead of drawing paths like this, it gets kind of messy, right? Like just 2 paths on here looks kind of confusing already. So what we do is we make a bijection. We say that, okay, let one step be represented by a letter. So let the step to the right be represented by R, and let the step up be represented by U. So each path has 2 R's and 3 U's, right? And I argue that every path in here corresponds to an arrangement of this word. So let's take the green path, for example. The first step is to the right, the second step is up, then to the right, then up, then up. Do you guys see how this is a rearrangement of this? So to solve this problem, instead of just drawing out all the paths, all we need to do is find the number of ways to rearrange this word. And how will we do that? Permutations, good. Does everyone understand permutations and combinations? So permutations of this word are how many ways can you rearrange the word, right? There are 5 letters in the word. How many letters can go in this slot? Let's suppose the R's and the U's are different letters. Or the 2 R's are different and the 3 U's are different. So let's say it's R1, R2, U1, U2, U3. So how many letters can go in this slot? 5. 4. Right, and this is equal to 5 factorial, as some of you already know. But the letters aren't different. R1 and R2 are the same thing, because right is right? There's no right 1, right 2. So to account for that, we need to divide by the number of permutations of the letters of the same letters. So how many, there are two rights, right? So what would we need to divide by to account for the rights? 2 factorial, right? Because there are 2 factorial to rearrange the 2 rights. Now how about the 3 ups? How many ways are there? 3 factorial, good. So what would this be equal to?
10.
10?
Yeah.
So it's, yeah, 10. So there are 10 paths from A to B. And do you guys see what the bijection is here? We basically made a bijection between a path and a word. And it's much easier to count the number of words than it is to count the number of paths. And after we determine the size of this set, which is the number of permutations of this word, we determine the size of this set, which is the number of paths from A to B. So any questions on how we did this? Okay, now let's take another example. How many of you are familiar with the term sticks and stones? Okay, so let's suppose we are playing a game. There are 4 people in the game, and everybody has a dice. And the purpose of the game is to get all 4 numbers. Oh, the dice is numbered from 0 to 6. So it's kind of a funky dice. And the purpose of the game is to get all 4 numbers to sum up to 6. So what is the probability that that team wins? Yeah.
Wait, so it's 0 to 6?
Right. Okay, so it's a 7-sided dice.
7 sides.
It's a funny dice, 7 sides. So let's say it goes from 0 to 6, and the purpose of the game is to get your 4 dice to sum up to 6. And we want to find the probability that you guys have a winning roll. Let's say you get a lot of money or something. So for probability, we know that probability is want over total, right? What are the total number of ways for you guys to roll your dice? 7 to the 4th, right? So this is the total number of different rolls you guys can have, because every person has 7 outcomes for their dice, right? And there are 4 people. So it's 7 times 7 times 7 times 7. And that's how we get 7 to the 4th. Okay, so now the main part of the problem is to find how many ways are there to get a winning roll. And instead of taking out dice and actually rolling them and looking at the numbers, we can just say, okay, so this is represented by A plus B plus C plus D equals 6, right? And A, B, C, and D represent the numbers on the dice. So A, B, C, and D can be 0, 1, 2, 3, 4, 5, 6, right? So the number of solutions to this equation, how will we go about finding that? It starts with a B. Bijection, right. Okay, so let's say the 6 that we want are represented by 6 stones. So this is where this term sticks and stones comes from. And we want to basically partition the stones into 4 different numbers, right? So we just draw, so to partition into 4 sets, how many dividers will we do? How many sticks? Only 3, right? So 1, 2, 3. And do you guys agree that this represents 1 plus 2 plus 2 plus 1 equals 6? So basically, every partition of these stones with sticks represents a valid solution to our problem, right? And you guys might argue, well, what if there's an empty pile? How will we represent that? What if somebody rolls a 0? So let's draw different examples. How will we represent the case where someone rolls a 0? Any ideas? Beth? do we do with the sticks? Yeah. So we put the sticks next to each other, right? If we put the sticks next to each other, then that means there's nothing in that set. So let's say 1, 2, and 3. Now what would this represent? What stone would this represent?
0 plus 3.
Well, 0 plus 0 plus 3 plus 3 equals 6, right? Because there's nothing behind this stone, and there's nothing in between, behind this stick, and nothing in between these two sticks, right? And this is 3, and this is 3. So do you guys see how this is working with the sticks and stones and the numbers? Every partition of the sticks and stones represents a solution to our equation. So now the question is, how do we find the number of partitions? Well, there are six stones and 3 sticks. And we basically just want to rearrange 6 stones and 3 sticks in any order, right? So there are 9 objects. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. And we want to choose 3 slots for this to put the sticks in. And once we put the sticks in, we can fill in the gaps with the stones. So 9 choose 3. What would that be? 9 factorial over 6 factorial times 3 factorial, or 9 times 8 times 7 over 3 times 2 times 1. That would give us 84 ways, right? So there are 84 winning combinations of the rules, right? And that would give us our probability. So I don't recommend playing this game. Your odds are not very high. But do you guys understand the bijection that was used in this problem? So we represented a solution to this equation by an arrangement of sticks and stones, a partition of sticks and stones. Okay. So now let's move on to a more advanced example. Let's say that you're playing the game, but there's another rule. Instead of summing up to 6, the rule is that you have 4 people, and you guys roll 1, 2, 3, 4 in a row. And the rule is that the second person's roll must be at least as large as the first person's roll. So if the first person rolls a 2, the second person has to roll a 2 or greater. And this applies for the third person and the fourth person.
Wait, is it still from 0 to 6?
Oh, okay. So the dice has turned normal for this game.
Oh.
They figured since you're having a more complicated game, they'll give you a normal dice. So the rule of this game is that each successive person has to match or top the last person's roll. So if we let the rolls again be A, B, C, D, let this be the first person, second person, third person, and fourth person, we know that the rules of this game is basically that A is less than or equal to B, less than or equal to C, less than or equal to D, right? This is what it means to match or top the last person's roll. And we know that A, B, C, D are between 1 and 6. So now we ask, what is the probability that you 4 will win this game? So with probability again, we're going to start with the total number of permutations, the total number of rolls. So how many is that?
6 to the 4th.
6 to the 4th, right? Because there are 6 possibilities for each person, and there are 4 people. So now is the hard part. How will we count the number of ways number of elements in this set. Number of elements A, B, C, D such that they satisfy these conditions. We notice that this sequence, we call this sequence a non-decreasing sequence. Does everyone see why this is non-decreasing? It can either stay the same or increase, but it can't decrease. So we want to find the number of non-decreasing sequences with elements from 1 to 6. But it's kind of hard to count non-decreasing sequences, right? Because you can't really use the slot method. You can't really say, okay, there's 6 possibilities here, which means there are 5 possibilities here. But every next element depends on the last element. So we can't just simply do this 6, 5, 4, 3 thing, right? What I propose is that we make a, starts with B, bijection, right? So what if I asked you, what are the number of increasing sequences from 1 to 6? Increasing sequence means that the elements go strictly in order. So 1, 2, 3, 4 is an increasing sequence. 3, 4, 5, 6 is an increasing sequence. 1, 1, 2, 2 is not an increasing sequence, right? So what is the answer to this new question? How many increasing sequences are there from 0 to 6? 3? 3? Which 3?
Oh, never mind.
Well,
You just do 6 to 4 because you pick 4 elements from the 6 that you have, and since combinations don't specify order, we can always order them as increasing.
right. So William says that, okay, give me a set of 6 numbers, let me just choose 4. There is only one way after I choose 4 to arrange them in a strictly increasing manner, right? So the numbers are 1, 2, 3, 4, 5, 6. So any 4 numbers I choose from here, I can arrange it in an increasing order. And the beauty of combinations is that order doesn't matter, right? So if you choose any 4 numbers, you get to order them. The combinations does not dictate order. That's the difference. That's the main difference between combinations and permutations. Because permutations is where order matters. You would say, okay, I'll choose the 3 first, then the 2, then the 1, then the 4. But in combinations, you can just say, okay, I'll choose the numbers 1, 2, 3, 4. It doesn't matter the order. So the number of increasing sequences from 1 to 6 that have 4 elements is defined by 6 choose 4. And what is 6 choose 4? 15, right? So look how easy that was. If it was just an increasing sequence, we could say, okay, 6 choose 4 is 15. 15 out of 6 to the 4th, this is a very crappy game, and we will not win, right? But that's not how it goes. Because this lets you have A equal to B, equal to C, equal to D. So what's valid in here is not necessarily valid here. We could roll 1, 1, 1, 1, and that would be a valid roll, right? So we now need to think of a way to transform this non-decreasing sequence to an increasing sequence, because we know that increasing sequences are much easier to count, right? Yeah.
We like run a set with 1, 2, 2 to actually work.
Yeah, that works for this condition. So we want to construct a bijection from this non-decreasing sequence to an increasing sequence. And now let's take a look at this set and think about how we might do that. how we eventually want something that says this: A is less than B, is less than C, is less than D. So how do we get from here to here? How do we make sure that A and B are not equal, B and C are not equal, and C and D are not equal? We can just modify the elements of this set, right? Let's say we add 1 to B. Now, do you see that B is greater than A? B is definitely greater than A. Because if B were equal to A, then it would be definitely greater than A now. So for C, let's add 2. Right? Now C is definitely greater than B. And what will we add to D? 3. So now we have constructed a bijection between this set and A is less than B plus 1, is less than C plus 2, is less than D plus 3. And this is exactly what we wanted. This is an increasing sequence. So how will we find the number of terms in this increasing sequence? What do these numbers even mean? What is D plus 3, right? So we begin by finding the range of numbers, because adding 3 to D changes the range of 1 to 6. Now, what is the range for our numbers? The minimum number is still 1, right? A can be equal to 1. But what is the maximum number? 9, right? Because if D were equal to 6, D plus 3 would be equal to 9. So we have turned the problem into how many increasing sequences are there with the numbers 1 through 9 with 4 elements. And how will we do that? How will we find that? I heard it. 9 choose 4. Good. Right? Because in each of these, in this 9 numbers, we can just choose 4, and we can arrange the 4 numbers in an increasing manner. So does everyone see how 9 choose 4 gives you the number of increasing sequences from 1 to 9, which in turn gives you the number of non-decreasing sequences from 1 to 6? So let's just do one specific example to maybe familiarize you more with what we did. So let's say we roll 1, 1, 3, 5. What is this biject to? 1 stays the same, right? What is this turning to? 2, 5, 8. Good. So do you guys see how this is a non-decreasing sequence and this is an increasing sequence? And every element in this set of non-decreasing sequences has a sister in the set of increasing sequences. And that is a one-to-one mapping, which is called a bijection. Are you guys starting to see sort of the power of these bijections? Yeah.
But doesn't any function just take one set of numbers and map it to another?
We are not talking about functions.
But a bijection is a function, right?
Yeah, you could think of a bijection as a function, but some functions are not one-to-one. A bijection is a one-to-one function or mapping. Like, you know how functions, sometimes they can have, let's say this function is not one-to-one. Because if we draw the horizontal line, we see that 2 numbers give you this value, right? Whereas this function is one-to-one. Because for every value of x, there is a distinct value of y. But in this, so this would sort of be the graphical analog to a bijection. Every element in x maps to one element in y. But in this one, every element in x does not necessarily map to a distinct element in y. So that is the difference between a bijection and a function. Okay, so back to our original question. Let's do one more example. What if we had 6, 6, 6, 6? Does this sequence match the conditions of our game? Yeah, because they're all equal, right? And they can be all equal by these conditions. So what would this map to?
6, 7, 7.
8, 9, right? So now these are just some examples to show you that, yes, this bijection does work. It takes an element from this set to an element from this set. And by counting the number of elements in this set, we've counted the number of elements in this set as well. So our final answer would be 9 choose 4, which is 9 times 8 times 7 times 6 times 5 over 4 times 3 times 2 times 1. 630, right?
You can't have to 5.
Why?
Because it's 4 and
Oh, it's 4. No, oh, right, you're right. Because you divide by 5 factorial and 4 factorial. So what would our answer be? 120. Yeah. Sorry, thank you for that. So 126 out of 64 is your probability of winning this game. Alright, now that we've covered sets and paths, let's move into something different. Let's talk about planting flowers.
Okay.
So you're a gardener and you have 3 tulips, 2 roses, and 5 daisies. And you want to plant your flowers in a row such that no 2 daisies are next to each other. So we have 3 tulips, 2 roses, and 5 daisies. You're going to plant these flowers all next to each other in a string of 10 flowers. And your only condition is that you don't want any 2 daisies to be right next to each other. So how many ways can I plant my flowers? How would we start? We want to start with the most limiting condition, right? Which is the daisies. The other, after you plant the daisies, you can plant the tulips and roses in any order you want, right? So how many ways are there to plant 5 daisies? Yeah. 2?
Because no 2 can mix each other.
Right, so we can have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. But what if I, instead of planting this daisy here, I plant it here? That also works, right? So we could try listing the possibilities because the daisies cover up, what, half the flower bed. So we could try listing the possibilities, but there's an easier way to do this with the bijection. So every arrangement of flowers in here, we want to biject that to a different arrangement that's easier to count.
So we can take the spaces that we want to put between the daisies, take those out, and find the number of arrangements.
Right, so William proposes, okay, let's take out these spaces for now. If we take out 1 space in between each daisy, then how many spaces do we have left to plant? So there's 10 spaces. If we take out 4, there's 6, right? 2, 3, 4, 5, 6. And this, taking out the spaces, would make all of them right next to each other, right? So this bijection has turned this arrangement of daisies, none of them next to each other, to this arrangement of daisies. And similarly, we can transform this arrangement to this arrangement by simply inserting a space in between each daisy. So how many ways are there to plant the daisies in this configuration, where there are no limit, there's no constraint on how we plant our daisies? Six, right? Because there is one extra space, and the one extra space can go in any of these 6 slots, right? So there's 6 ways to plant the daisies. After we plant the daisies, here we just insert one space in between each daisy, and we have satisfied the conditions of the problem. Alright, so now that we've established that there are 6 ways to plant the daisies, let's say we plant a daisy here, 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 and here. Now all we have to do is fill in the tulips and roses, right? And there are 5 slots remaining for the tulips and roses. And this is a simple combination problem, right? There are 5 slots. You choose 2 of them to put the roses in, and then you fill in the others with the tulips, right? So that would be given by 5 choose 2. So our final answer is 6 times 5 choose 2. 6 for being the number of ways to arrange the daisies, and 5 choose 2 being the number of ways to arrange the rest of the flowers. So numerically, what does that give us? 6 times 10, which is 60, right? So there are 60 ways to plant your flowers. Okay, so there's one more strategy that I want to show you with bijections, and that involves counting rectangles. So let's say you have a grid that looks like this. And you're asked to find the number of rectangles in this grid. How would you guys go about doing that? Yeah.
Well, I would just like find out how many rectangles are made up of one rectangle, and how many rectangles are made up of 2 rectangles, and how many rectangles are made up of 3 rectangles, and then just add them up.
So you want to basically do this in casework, right?
Yeah.
The different types of rectangles, how many are there? So, but there are a lot of different shapes for the rectangles, right? You can have one that looks like that, one that looks like that, one that looks like that, one that looks like that.
What about only 2?
Only 2, yeah. So I'm just showing you the examples of rectangles that you have. And then so you would have to start by finding the different types of rectangles, and then going back and counting, right? So this casework method, it will definitely work, but it will take quite a bit of time to find the number of rectangles and then count them. So we can turn this into another bijection problem. What is a rectangle defined by? It's defined by its 4 sides, right? Its 4 boundaries. So let's just choose an arbitrary rectangle in here. Let's look at this rectangle. Oops. Okay. Do you see how this rectangle here is defined by this side, this side, this side, and this side? Now, let's extend those sides. Let's extend this side to cover this line, and this side to cover this line. Let's do the same with here here. So, do you guys see how this rectangle is defined by these 4 lines? Which are different lines in this grid, or whole lines in the grid. So to count the number of rectangles, we just need to figure out how many arrangements of these defining lines there are, right? Let's first look at the green lines. How many ways are there to choose 2 of these green lines from this side, from the base? How many ways are there to choose the 2 green lines? Well, how many lines are there in the base? 1, 2, 3, 4, 5, 6, right? And we want to choose 2 of them. So what would that give you? 6 choose 2, right? So 6 choose 2 for the green lines. How about for the red lines? There are 1, 2, 3, 4, 5 red lines, and you want to choose 2 of them. So that would be 5 choose 2. So the total number of rectangles would just be 6 choose 2 times 5 choose 2, right? Instead of counting rectangles, we'll just count their defining boundaries. And this would give you 15 times 10, which is 150. That would suck to have to count 150 rectangles. So do you guys see how this bijection simplifies the counting of these rectangles? Alright, so now that we've covered rectangles, we've covered dice, let's look at sets one more time. Suppose I have the numbers 1 through 50. And I want to find the number of subsets that consist of consecutive numbers. So a subset that satisfies this would be 1, 2, 3, or simply just 3. This is defined as a consecutive subset, because this is kind of a trivial example. But 1, 2, 3, 3, we could have 8, 9 as a consecutive subset. And we want to find the total number of consecutive subsets in this set of 50 numbers. So in this case, we could also go about casework, right? Okay, how many subsets are there with just one element? There's 50 for 3. How many subsets are there with just 2 elements? How many for 3? How many for 4? So we could do that from 1 through 50. Or we could look at the numbers in a slightly different way. So the beginning and the end of a set, these brackets can sort of be seen, this can sort of be a sticks and stones problem, right? There are 50 stones and we want to partition them. We want to drop 2 sticks to define a consecutive subset. Right? So how many ways can we do that? How many dividers do we have, first of all? 2, right? The beginning and the end of the set. But can we put the dividers right next to each other, like we did for sticks and stones? No, because we can't have an empty set. So what we have is an arrangement of 50 stones and 51 spaces to put the sticks, right? So we can put a stick in between any 2 or before any stone, right? So you put a divider here and a divider here, and this would define a consecutive subset. So this would be 2, 3, right? Or we can put a divider here and a divider here. And that would be 1, 2, 3, 4, right? So to count the number of consecutive subsets, we just need to count the number of ways we can divide these 50 stones with 2 sticks. So how many ways are there to do that? 51 choose 2, right? Because there's 51 slots for the sticks and there's only 2 sticks. So that gives you 51 choose 2, which is 51 times 50 over 2, right? Okay, so in the last part of class, we'll take a look at some example problems. Give you guys the handout. Please go to page 2 and look at the problems. So the back of the front page, because we've already covered the basic strategies for these problems. So let's look at this page. This is page 202.